Hello, I am JD and you're listening to The Ongoing. Right now, as you listen to this, invisible waves are passing through you, through the walls, through the air, through your own body. You can't see them, you can't feel them, but they are there. And they are carrying information, music, voices, data. This episode is about those waves, where they come from, and how we ever came to know that something so invisible could even exist. It's a big story, so we will tell it in two parts. In this first part, we discover what a radio wave actually is and how we proved it was real. In the second, how we learned to ride these waves and connect the whole world. But it begins with a simple question: what is a radio wave? To answer that, we go back to two forces people had known about for a very long time: electricity and magnetism. For most of human history, these seemed like completely separate things. Electricity was sparks and lightning. Magnetism was the force in a magnet, the pull that turns a compass needle north. There seemed to be no connection between them. And for a long time, no one thought there was. But in the early 1800s, small clues appeared. When an electric current flowed through a wire, a compass needle nearby would move, as if a magnet were close. So electricity could create magnetism. And the opposite was true too. Move a magnet near a coil of wire, and a current would start to flow in it. So magnetism could create electricity. The two were connected somehow, but nobody yet understood how deeply. That understanding came from a Scottish physicist named James Maxwell. In the 1860s, Maxwell did something different. He did not run a single experiment. He worked purely with mathematics, taking the observations other scientists had made and working out the equations that tied them together. And in that math, he found something nobody expected. Electricity and magnetism were not two separate forces. They were two sides of the same thing. And together they could make a wave. To understand how, we need to understand one simple idea: a field. A field is just the invisible area of influence around something. Bring a paperclip close to a magnet, and it gets pulled in. That invisible region around the magnet where its pull is felt is the magnetic field. Electric charges have the same thing. The space around a charge where it can push or pull on others is the electric field. So, a field is simply the invisible reach of a force. Now, here is what Maxwell realized. When an electric field changes, it creates a magnetic field. And when a magnetic field changes, it creates an electric field. Notice the key word in both, changing. A field sitting still does nothing. But a field that is changing creates a new field of the other kind right next to it. And that is where something wonderful happens. Give an electric charge a sudden shake. That disturbs the electric field around it. And because the field is now changing, it creates a magnetic field beside it. But that magnetic field doesn't appear and hold still. It grows from nothing up to full strength. And while it grows, it is changing. So it creates a new magnetic field a little further out. And that field is changing too, so it creates another magnetic field. Each one gives rise to the next, over and over, moving outward through the space. A ripple that carries itself along. It needs no wire, no water, nothing to travel through. Once it begins, it keeps building itself as it goes. That self-sustaining ripple is an electromagnetic wave. And a radio wave is simply one kind of it. But Maxwell math told him one more thing: how fast this wave should travel. When he worked out the speed, a number came out. And Maxwell recognized it at once. It was the speed of light. This stopped him cold. There was no reason a wave of electricity and magnetism should travel at exactly the speed of light, unless light itself was one of these waves. And that was his stunning conclusion. Light is an electromagnetic wave, the very same kind of ripple of electric and magnetic fields. Now think of ripples spreading across water. They rise and fall, up to a peak, down to a low, over and over. Every wave does this. And how quickly it rises and falls has a name. We call it frequency. Light and these invisible waves are the same kind of thing. They just have different frequencies. It was a beautiful theory, but it was for the moment only a theory. No one had ever produced one of these waves or caught one, and plenty of scientists doubted they were real at all. Maxwell himself died in 1879 at just 48 without ever seeing his waves proven. The proof would come from someone else. That someone was a young German physicist named Heinrich Hertz. In the 1880s, Hertz set himself a single goal. Could he take Maxwell's predictions off the page and make it real? Could he create one of these invisible waves and catch it somewhere else with nothing connecting the two? The experiment he designed was beautifully simple. Let's start with how he sent the wave. To make a wave, you need an electric charge that changes very quickly. And there is an old familiar way to do that, a spark. When a spark jumps across a gap, it is a sudden rush of electric charge, surging back and forth at tremendous speed. Exactly the kind of fast change Maxwell said would throw off a wave. So Hertz built a sender that released a spark, jumping across a gap between two metal knobs. Every time that spark cracked, if Maxwell was right, it should send an invisible wave rippling out into the room. Now, the harder problem. How do you catch an invisible wave? For this, Hertz built a receiver that was almost absurdly simple. A loop of wire with its own tiny gap. His thinking was this: if a wave came across the room, it would carry changing electric and magnetic field with it. And when those fields washed over the loop of wire, they should push the charges inside it. And if the push was hard enough, it would force a tiny spark to jump across the gap in the loop. So picture it. On one side of a dark room, a sender throwing off sparks. On the other, a plain loop of wire with a gap. And between them, nothing at all, just open air. If a spark appeared in that far loop, it could mean only one thing. Something invisible had crossed the empty space between them. A wave. In 1887, Hertz ran the experiment. He set off the spark at the sender. The gap crackled and snapped. And across the room, in the tiny gap of that lonely wire loop, a faint spark flickered into life. Nothing connected the two, and yet, when one sparked, so did the other again and again. An invisible wave had crossed the room and stirred the charges in a loop of wire on the far side. Maxwell's predictions, waiting quietly inside those equations for more than 20 years, was real. Hertz studied it carefully to be sure. He bounced the waves off a metal sheet like a light off a mirror, and when he measured their speed, it was the speed of light. Every test agreed with Maxwell. These invisible waves were real, and Heinrich Hertz was the first person ever to create them, catch them on purpose. And yet, here is the most surprising part of the whole story. Hertz did not think his discovery was good for anything. When people asked him what these waves could be used for, he is said to have answered plainly that they were of no use at all. To him, it was simply a way to prove Maxwell right. He had no idea the faint sparks crossing his laboratory would one day carry voices across oceans. Let millions hear the same music in the same instant. Connect nearly every person on earth sitting in their pocket without a single wire. He could not see that he had just struck the first spark of the entire wireless world. And that is where we will pause today. In the next part, someone finally sees what it could become. We will follow how we learned to ride these waves and how a spark in a laboratory grew into the invisible signal humming all around you right now. That's it for today. Thanks for listening. I am JD and this is The Ongoing.